Okay, welcome to this second focus day for FRQs. Today we are focusing in on F prime and F double prime graphs, which we did these in Unit 3. As with the other focus day, after today, after we do a couple of these, they are going to start working their way into your homework, so we're going to continue to practice these over the next couple of weeks. Additionally speaking, there is at the back of the PDF attached to these notes a third FRQ for anyone who would like to do another one. It comes out of 2014. And remember, that's something that you could just do on your own if you wanted. I'd be happy to send you either the answer key or a video walking through it. Or you could bring it to office hours or whatever, and we could do it together there if you wanted. So as I talked about last Monday, I will always include that third FRQ for anyone who would like to use it. Okay? But here we go. So we're going to do this one. First one, more so mine. Second one, I would encourage you to make it a little bit more yours, if you wanted my recommendation. Although both will be, as with the last Monday, fairly heavily guided by me, because I'm using them as my reteach. So with our FF prime, F double prime graphs, ladies and gentlemen, the first thing that we would have looked at in Unit 3, and I would have tried to emphasize quite a bit, is being careful to take a strong and very purposeful notice about what graph you're looking at. In this case, we're looking at a graph of F. Because depending on what graph you're looking at, that's going to change potentially the information that you pull from it, right? If we're looking at a graph of F and asked about concave up, well, we'll look for a cup. But if we're looking at an F prime graph and asked for concave up, we're going to look for F prime to be increasing. F double prime, we want F double prime to be positive. Vice versa for concave down. And then points of inflection occur right here in the middle. I'll put POI in the middle. Similarly, for F increasing, if we're looking at a graph of F and wanting to know where it's F increasing, we'll look for it to go up. F prime, we want to see a positive. Going down would be negative. And so a change from positive to negative would be the location of a relative max. Vice versa for a change from negative to positive for a relative min. Right? And so again, you want to be very careful about taking note of specifically what graph we are looking at here. This is a graph of F. The figure above shows the graph of a piecewise linear function F between -4 and 12, and we are told that the function g is defined by g of x equals the integral from 2 to x of f of t dt. We did one of these last week, but and we're doing it again today so that I can make a very particular recommendation, and I would highly recommend writing it down into your study notes, which is the minute you see an integral function like this and you're looking at a graph, take the derivative. Do it immediately. That comes, I would say, ladies and gentlemen, more just from my experience, right? As a teacher, I get to share that experience with you. When you are looking at a College Board FRQ, if you see a function that is an integral, and especially if you're looking at a graph, but the minute you see a function that is an integral, take the derivative, use second fundamental theorem of calculus, because I would say 8 to 9 times out of 10, you end up needing that derivative at some point. So before I do anything else with this problem, down here in part A, I'm going to take the derivative of g. So taking the derivative of a function that is an integral, that's second fundamental theorem of calculus. So we're going to take our upper, plug it in, times the derivative of the upper. Derivative of x is 1, minus take the lower, plug it in, times the derivative of the lower, the derivative of 2 is 0. And so my g prime of x equals f of x. This particular year, ladies and gentlemen, if you look at the rubric, there was a point awarded for having g prime of x equals f of x, for writing that down, and they gave you that point whether you wrote it down in part A, B, C, or D. If at some point you wrote that g prime of x equals f of x, if at some point you used second fundamental theorem of calculus to generate that fact, you earned a point. And so again, I highly recommend do it immediately. Do it as your first step. Even if you don't think it's going to be necessary for part A, put it down anyway. Put it into your problem so that you have it there to reference. Because what that means is that while I'm looking at a graph of f, I'm looking at the first derivative graph of g. I'm looking at g prime. And part A asks us, does g have a relative minimum, a relative maximum, or neither at x equals 10? And justify your answer. Okay, well, going back to Unit 3 for a function, in this case g, to have a maximum, its derivative, in this case g prime, would need to change from positive to negative. That's what we wrote here, right? Maximum, the derivative needs to change from positive to negative. For g to have a relative minimum, its derivative needs to change from negative to positive. Right? Minimum would be negative to positive switch. And then neither, you wouldn't see, well, either of those happen. So at x equals 10, which is here, does my g prime, I'm looking at g prime, does my g prime change from negative to positive, positive to negative, or neither? And in this case, it's neither. Because my g prime here was negative to the left, right? It's below the x-axis to the left of 10 and still below the x-axis, still negative to the right of 10. I have neither at x equals 10 because g prime, which is my graph of f up here, does not change sign at x equals 10. So when you're looking at derivative graphs, minimums are where the first derivative changes from negative to positive, maximums are where they change from positive to negative. Okay, part B. Does the graph of g have a point of inflection at x equals 4? Okay, so you're thinking about, well, for a graph of g, I know what a graph of g, a point of inflection would look like, but I'm not looking at a graph of g. I'm looking at a graph of g prime. So on a first derivative graph, what does a POI look like? On a first derivative graph, a point of inflection is where the graph changes from increasing to decreasing or decreasing to increasing. So on this g prime of graph at x equals 4, which is right here, do I see my first derivative graph, this g prime graph here, change from increasing to decreasing or decreasing to increasing? And yes, right, this g prime graph is increasing and then decreasing. So my answer is yes, because my g prime graph, which is this f graph, changes from increasing to decreasing at x equals 4. Okay, part C, we have find an absolute minimum and absolute maximum value. So we did one of these last week already, and I made the recommendation at the time, but I'm going to say it again today, that when you see, especially on an FRQ, you see a problem that asks you to find absolute maximums and absolute minimums, I would do the first two steps first. Move on, do the rest of your FRQ problems, do all of the faster ones that you know how to do, grab those points, and then come back and finish the absolute extrema at the end. Because absolute extrema, you get one, sometimes two, a lot of times only 1 point, but sometimes two, for your final answer, which is there's a lot of work involved in getting that final answer, which for only 1 point, you have to choose how are you going to maximize the time spent or minimize the time spent to maximize your points, right? You want to use as little time as possible to earn as many points as you can get. So you come back and finish this problem at the end. What you should, though, as I said, should do at least is the first two steps, like we reviewed last week already. Absolute minimum, absolute maximum. We're going to start by taking our derivative, which we did that up above. Here's my f of x. And we're going to set that derivative equal to 0. All right, this derivative here, I'm going to set it equal to 0. Because sometimes you get a point in and of itself just from that step. Unfortunately, this year you didn't. But sometimes you do, and so it's a good one to make sure you have that down. And then step 2, we're going to identify, well, where would those zeros be? What are going to be my candidates? So in this case, where does this G prime graph equal 0? Well, this G prime graph equals 0 at -2, 2, 6, and 10. And then you take those numbers and your endpoints and you plug them into your original function. We're not plugging into G prime, we're plugging into G. So we're going to be plugging the -4, the one endpoint, into G, plugging in -2, 2, 6, 10, and our other endpoint was just 12 to figure out which one of those values generates the largest value and the smallest value for my absolute max and absolute min. And that right there, ladies and gentlemen, is the point that I would move on. At this point, with that work, you earned 2 points on this year. Some years you might have earned 3 points. This year you earned 2. And so like those 2 points are fairly quick to earn, as opposed to the last part of the problem, which takes a while. So you'd move on, you'd do the rest, and you'd come back to it at the end. Okay? We're going to go ahead and finish this one out because it is my reteach. Okay, so plugging in our -4, my g of x function is the integral from 2 to x of f of t dt. So we're plugging in the integral from 2 to -4 of f of t dt, which is upside down, so we're going to fix that. And so we're looking here at the areas from -4 to 2 of my function, and then multiplying it by a negative. Okay, so from -4 to 2, -4 to -2 is this triangle here, which is negative. It has a base of 2 and a height of 4. So -1/2, base of 2, height of 4. Going all the way to 2, so we've got this triangle as well, right here, which is 1/2, base of 4, height of 4. Right? Which equals, this would be -4 plus 8, which is 4, times the negative would be -4. And you do it again for -2. 2 to -2, which is upside down, so let's fix it. -2 to 2. So negative times the region from -2 to 2, which up here would be just that triangle right there. 1/2, base of 4, height of 4. So -2 to 2 would be 1/2, base of 4, height of 4, which is 8 times a negative, which is -8. 2. The integral from 2 to 2 of f of t dt is 0. 6. The integral from 2 to 6 of f of t dt equals, that's not upside down, so we don't have to fix anything. So we're coming up here. We're doing the integral from 2 to 6, which would be this area right here, which is a triangle. 1/2, base of 4, height of 4. Which gives us 8. Okay, 10, we have the integral from 2 to 10 of my function, which is that same triangle we already did, right? 2 to 10 still has that same triangle we already figured out, but also has the second triangle, the rest of the way going all the way to 10. That's this guy here, which is negative. Has a base of 4 and a height of 4. So we would have 8 minus 8, which is 0. And last but not least, our 12. Going all the way to 12, includes those same two triangles we already figured out, 1/2 base of 4 times height of 4, negative 1/2 base of 4 times height of 4. Whoops, and we've got one more triangle. So we've got these two triangles going from 2 to 12 that we already figured out. And one more negative triangle here, which has a base of 2, height of 4, negative because it's below the x-axis. Plus here, which gives us 8 plus negative 8 plus our negative 4, which is negative 4. And so my absolute max is negative 4, negative 8, 0, 8, 0, and negative 4. My absolute max is 8 at x equals 6. And my absolute min is, let's see, negative 4, negative 8, 0, 8, 0, negative 4. Negative 8 would be my smallest, which occurs at x equals negative 2. Okay, last one. Part D here asks you on negative 4 to 12, so we've just found all of these values here. On negative 4 to 12, for what intervals is my g of x less than or equal to 0? So negative or equal to 0, so we're going to be doing brackets here. Okay, so starting at negative 4, my g of negative 4 here, right? My g is negative. So negative 4 would be less than. And then we're negative, negative, and then 0. So we stop at 2. Next 2 is 0. And then we're positive, and then 0 again. So we're picking up again at 10. And going to 12, which is the end of my interval here, which is negative. And these ones would have to be brackets because they specify that it's or equal to. So you would need brackets there. Okay, one more here, ladies and gentlemen. We have another f prime, f double prime graph. My recommendation, make this one a little bit more so yours. We have the figure above shows the graph of f prime, the derivative of a twice differentiable function f on the interval negative 3 to 4. The graph of f prime has horizontal tangents at negative 1, 1, and 3. The areas of the regions bounded by the x-axis in the graph of f prime on the intervals negative 2 to 1 and 1 to 4 are 9 and 12 respectively. Okay, so pause for a second. Pause the video if you need to. And what important information were we just given in that paragraph? Okay, well, important information. Again, pause the video if you're not done yet. We need to make sure we take note of what graph we are looking at. We are looking at f prime. We know that we've got horizontal tangents at negative 1, 1, and 3, which means that's going to be what I call those 3 points. If I ever need to reference that minimum right there, it's negative 1. If I ever need to reference that maximum, it's at 1. That minimum, it's at 3. Okay? And then our regions from negative 2 to 1 is, well, they tell us 9, and they tell us 1 to 4 is 12, but we have to go, oh, no, it's not. Back in Unit 3, when we first learned this, I would have said there are times where College Board, quote unquote, helps you out and says that area is 9. And you have to say, I hear you, but actually I know it's negative 9. Why do I know that that region is negative 9 and that region is negative 12? Because they're below the x-axis, right? So you have to be careful of that. I know it says they're 9 and 12. Like we talked about back in Unit 3, they're going to quote unquote help you out. That region's 9, that region's 12, and you have to say, oh, nope, you can't fool me. It's below the x-axis, therefore negative. Okay? Okay, so now we're going on to Part A. Part A, find all x coordinates at which f has a relative maximum. Give a reason for your answer. Pause the video if you need to. Where does f have a relative maximum, and how do you know? Okay, Well, for f to have a relative maximum means I'm looking for a hill. However, this is not a graph of f, so it's not going to look like a hill. This is a graph of f prime. So what does a relative maximum look like on an f prime graph? It's a change from positive to negative. So on this f prime graph changes from positive above the x-axis to negative below the x-axis at -2. And then why? Give a reason, because, and it's exactly what you just said. F prime changes from positive to negative at x equals -2. Okay, part B. On what open intervals contained between -3 and 4, and look at no equals. So for 2 reasons, we know we are going to be writing our answers here as open intervals. Make sure we're careful about that. So on what open intervals between -3 and 4 is the graph of f both concave down and decreasing? Pause the video if you need to. Okay, for f to be concave down, we'd be looking for a frown shape if I was looking at an f graph, but I'm looking at f prime. So what does f concave down mean on an f prime graph? It's decreasing. F decreasing means going down if I'm looking at an f graph, but again, I'm looking at f prime. So what does f decreasing look like on an f prime graph? And that would be f prime is negative. So I want this f prime graph to be both decreasing and negative for my answer, which is from -2 to -1. Oops, my pen is dying. Sorry, one second. -1 and 1 to 3. And then your reason is those definitions. Is decreasing and negative on those 2 intervals, -2 to -1 and 1 to 3. Okay, C. Find all x coordinates of the points of inflection for the graph of f. Give a reason for your answer. Pause the video if you're going to do so. Okay, well, an f point of inflection is a change in f from concave up to concave down or concave down to concave up. But again, I'm not looking at a graph of f, I'm looking at a graph of f prime. So what does that mean about f prime? What is f prime doing? F prime is changing from increasing to decreasing or decreasing to increasing. So what x coordinates is f prime changing from increasing to decreasing or decreasing to increasing? Okay, well, it'd be at -1, 1, and 3. And then your reason, so there's lots of ways you can write your reason. When I did this one, I split it up. -1, 1, and 3. I said because f prime changes from increasing to decreasing, at x equals 1, and changes from decreasing to increasing at x equals -1 and 3, which is not the only way of potentially phrasing that, but it's your reason. How do you know? Okay, which brings us to part D, our fourth and final one here. Part D of this particular year is the one that's a little bit weirder. Still comes directly from your notes though. So honestly, even in 2015, all four of these do come directly from your notes. Why I classify D as the weird one is not because it's not in your notes. It very clearly is. It's because it's not from Unit 3. A, B, and C all come directly from Unit 3, 3.6 in particular. D actually comes from 7.4. In D here, it says given that f of 1 equals 3, write an expression for f of x that involves an integral, and then use that to find f of 4 and f of negative 2. So not only does this one come directly from your notes, ladies and gentlemen, they even give you a little bit of a help here, a hint, I should say, as to exactly how you're going to write this expression, exactly how you're going to find this f. What this is the desired position formula from 7.4. We use the desired position again one more time anytime you have one position and you're looking for a different one. And so even without this phrase right here, we know that this is the desired position formula because we have one position and we want a different. Our given position in this particular case would be 3. The time corresponding to that position would be 1. And the time at which we're trying to find for this guy would be x. But again, eventually we're going to end up plugging in 4. So we can figure out what it would be at 4. That's the time at which we're trying to find our position, and then negative 2. So 1 to negative 2, the time at which we're trying to find our position. So that's why we know even without this phrase. Now again, they gave you a helpful hint, and they even told you that it's going to involve an integral of some sort. And so it gives you, like I said, just kind of that other insight into why we're using the desired position formula. Okay, so again, given position, time corresponding to that position goes on bottom every time, and the time at which you're trying to find your position will go on top. Okay, and so then evaluating this, we have 3 plus the integral from 1 to 4, so the area from 1 to 4 is negative 12. Gives us negative 9 as our answer. And down here, this guy's upside down, so let's fix that. Make it negative. Maybe negative 2 to 1. And so we have 3 minus the integral from negative 2 to 1 is negative 9. Which gives us our final answer of 12.